In section 4.5, we're going to talk about tree and Venn diagrams. And this just gives us a nice kind of visual representation to get some outcomes and experiments and to even calculate a couple probabilities. So let's start off with an example here where we're picking some balls from an urn. And we're going to do this with replacement. So we're selecting, there's 11 balls in there, 3 are red and 8 are blue. And so we're going to go ahead and select 2, one at a time with replacement. And so on our first draw here, what's possible in order to get is we could either get a red or a blue ball. Now when we go to the second draw, we're going to have the same thing. You could either get a red or blue or a red or blue, depending which one we had. So this is kind of a diagram to just get all the outcomes here. So our sample space would consist of red, 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 blue, blue, red, or blue, blue. Now the sample space has to consist of all the possible outcomes. So red, blue will be different from blue, red. Okay. An event could be that we get one red and one blue, and that'll treat them the same. But the sample space has to account for every single outcome. And let's go ahead and put our probabilities here. So if we pull a red ball, it's going to be 3 out of 11 because there's 3 out of 11 balls there. And then for the blue, there's 8 of those out of the 11. Now, since we're doing it with replacement here, it's going to be the same thing on the second draw. We're going to go ahead and put the ball back in, shake it around. And so we're still going to have 3 out of 11 to get a red and 8 out of 11 to get a blue. If we wanted the probabilities of getting each of these sample spaces here, so probability of R and R, that's going to be the probability of R times the probability of R because it's independent in this case here. Okay. So it doesn't matter what happened before. If we're doing the AND case, we're just going to multiply probability of one times the probability of the other. And so that's going to give us 3/11 times 3/11. Let's go ahead and go to the next one. Probability you get red and blue. And again, when you get a red, it doesn't matter what happened before. When you go to get the second ball, it doesn't matter what happened in either case. So we're always replacing them back. This is going to be the easier case here. And so we'll go ahead and list the probabilities for all of these. Every time we select a marble, we put it back in or a ball, and then we shake it back up. Okay. So let's look at the same example here. But let's consider the case now. Instead of with replacement, why don't we change that to without replacement? Let's do a dependent case. And so the first draw is still going to be red or blue. And for the second draw, again, we could still get red or blue. Our sample space is not going to change. We could still get red, 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 blue, blue, red, blue, blue. But our probabilities now, what's going to happen here is we have 3 out of 11 for red and then 8 out of 11 for blue. So let's consider the first case where we selected an actual red marble. Now for the second draw, since we're doing it without replacement, that means that there's only 2 red marbles left out of 10 because I took one out. I didn't put it back in. And for blue, well, you still have all 8 blue marbles, but only out of 10 because there's one less overall. If we go the other route where we pull the blue one first, then we're going to have 3 out of 10 red and 7 out of 10 blue. So this is what we call without replacement or the dependent case. It matters what happened before. And I'm going to use a subscript of 1 and 2 to indicate the first selection and the second selection here. So probability of R1 and R2 is the probability of R1 times the probability of R2. But we have to consider given that R1 already occurred. And so if we multiply those, we'll get 0.05 and 45. Again, the nice thing about this tree diagram is that you just have to multiply them following the path that we have here. So 3/11 times 2/10. And let's try these out for all of them. Again, here, following this path, so 3/11 times 8/10 will give us that probability. And we could try these out for all of them here. And again, following the paths here for that one and for blue as well. So this tree diagram gives us a nice way to get the probabilities, the sample space, and just organize everything. Let's look at Venn diagrams here. And we've already kind of looked at some of these, but this is just a nice way to get a picture of the information, so to organize. So here we have an experiment with outcomes from 1 through 12, and we have a couple of events. So event A, that you're the numbers 1 through 6, or the integers. Event B, that you have 6, 7, 8, or 9. And then we could see that the AND case is 6, because that's what's going to be what's in common between these two. And then the OR case, just getting all of them. So 1 through 6, and then adding any additional values that weren't already included there. So let's first draw A here. And inside of A live integers 1 through 6 here. And then here's B. And so in B are 6, 7, 8, 9. But notice since 6 is in both of them, that's going to be right in the center, that overlap. And we also want to make sure we write the sample space, because there are some values that are not in events A or B. So the entire sample space here, denoted by S, the numbers we are missing are going to be 10, 11, and 12. So they live in the sample space, but outside of events A and B. And so this is a nice diagram of the events that's listed. And these guys are not mutually exclusive. Note, mutually exclusive, you could also have events that are disjoint, right, where there is no overlap, and probability of A and B will be equal to 0, because there's no overlap between those two. In section 4.6, we'll be talking about counting techniques, combinations, and permutations. So let's start off with the multiplication rule here, which tells us that if we're doing multiple events here, we just have to multiply them together. So let's look at this example where we have a choice of 3 salads, 8 main dishes, and 5 desserts. So how many different meals consisting of 1 salad, 1 main dish, and 1 dessert are possible? So if we're trying to select from there, how many different possible outcomes could we have here? So let's look at it selection by selection. So for the first selection, we have salad, and there's 3 choices. For the second selection, the main dish, we have 8 choices. And for the third selection, we have dessert, and that's going to be 5 choices. The multiplication rule tells us we just have to multiply those, and that'll give us the total number of outcomes that we have. So it's going to be 120 meals. Let's take a look at permutations here and combinations. And so here's a notation. We'll usually say here for the permutation, n pick x, or we might say for this one, n choose x for the combinations. And we'll first talk about that factorial notation, that exclamation point here. But the permutation, we're going to say that order matters. And for combinations, order does not matter when we get those. So what is this factorial? And so factorial is an operator. What this tells us is we multiply that integer times every integer below it till we get to 1. So for example, 5 factorial would be 5 times 4 times 3 times 2 times 1, which will give us 120. Let's try to calculate a permutation here. So pick 3 here. And this is going to give us 5 factorial over 5 minus 3 factorial. And so if we clean that up, that's going to be 2 factorial in the denominator. And let me expand this out a little bit. This is saying 5 times 4 times 3 times 2 times 1. And in the denominator, we can make factors of 1. And so that's just going to end up giving us 60. So we'll multiply whatever's left over. Let's do a combination here. So same idea. And sometimes we might use this bracket notation. So 5 choose 3. So if we plug this into the formula, it's 5 factorial over 3 factorial. And then an easier way to kind of remember what goes in the denominator to not get so caught up on the formula is that on top we're going to have 5, and in the denominator we're going to have 3, and then whatever other value adds up to 5. So 3 plus 2 should give us the 5 there. And so let's expand this out. On top, I'm going to go 5 times 4 times 3 factorial. And the reason I'm not expanding 3 times 2 times 1 is because the denominator also has it, and I could create that factor of 1 very easily. So that'll end up giving us 10 in this case. So for the order matters and permutations, if I'm going to select 3 from 5, every single way, if I select a book first or second, the way I get them makes a difference. For a combination, it does not make a difference. If you're going to serve yourself mashed potatoes, turkeys, and peas, it doesn't matter if you get peas, mashed potatoes, and then turkey, or turkey, peas, and then mashed potatoes. The order doesn't matter. So that's what a combination would just say. As long as you have those 3 items, we'll call it as one set there. The permutations is going to worry about the order that you got them in. And we do have a function on our calculator to help us out with that. Under math, you'll go over to the right and you'll see probability. And there's NPR and an NCR. They use R rather than X for their variable. And there is also a factorial button. So we don't even have to plug these whole calculations in. Let's try out this example here. And so the key thing to note is that order matters here because we're picking 3 different officers here. So it makes a difference if you're president, vice president, or secretary. So your role is going to make a difference here. So we're going to go ahead and do 15, pick 3 here. And we'll go ahead and clean this up a little bit. And that's going to give us 2730. Again, because order matters. It makes a difference here. Well, what if we do the same thing in a club with 15 members, but this time we just want to pick a committee of 3 people. So there are no positions assigned. So if you're selected, you're on the team. There is no ranking in there. So in this case, order does not matter, and so it's going to be a combination in this case. And so 15 factorial over 3 factorial times 12 factorial. And so notice that the combination here has this additional 3 factorial. That's eliminating all the ways that they could count those groups of 3. So we don't need them to overlap. Once you have the 3 in a group, we're counting it. So again, it doesn't matter how they were selected. If you pick A, B, and C, or B, C, and A, they're counting those as the same way there. And so it's going to be significantly less. You can notice that it's this number here divided by this extra amount.